the talk itself is structured in two pieces. In the first part, I want to just give you a brief heads up what the mission is about. And then in the second part talk actually about the results that we published in SIGMOD VLDB last year, which are, let's say, the highlight that we present here in this talk. So what is this project that I'm working in the decentralized cybersecurity mission about? It's about federated machine learning and making it more trustable. But in order to understand what we are working on, let me give you a brief introduction into federated machine learning and bring everybody on the same page. So what is federated machine learning? The idea of federated machine learning is to jointly learn a machine learning model between parties or peers that do not necessarily trust each other. And the benefit over centralized machine learning approach is that every of those peers can keep the training data local, and only model updates need to be shared between the peers. This has many applications. As I said, for example, if you don't want to move your data and privacy is an issue, then federated machine learning is used very often. And this can be done in many application domains, like in a medical domain, for example, for learning an image classification model, where the different hospitals might share or might want to learn such image classifier based on medical image records. They could keep the data local and train this global model in using federated machine learning. And there are many more application domains where this is an issue. For example, if you want to train a model across data from different mobile phones from private end users, federated machine learning is also used today. So how does federated machine learning work? Just a quick intro into that in one slide. So the idea is that every peer trains a local model. If he has sensitive data, like, for example, his cat and dog images, in order to train here a classifier that can differentiate between cats and dogs. And this is done on every side. Every peer trains a local model. And then in a second step, for every epoch, the peer sends his updates to a global parameter server that aggregates the updates. The peers read back the global information or the global model, and then the next round of training starts. And this works pretty well, but unfortunately, there are a lot of possible attacks that have been detected in federated machine learning. And let me go over the typical classes of attacks that we see in federated machine learning approaches. One are so-called peer-side attacks, and they work in a way that one of the peers maliciously falsifies the data that he uses for training. So he mislabels image data, or he just sends erroneous model updates to the central server. And the goal here is to, let's say, lower the quality, the accuracy of the trained model such that it gets unusable by the other peers, or that it misclassifies certain situations. The second class of attacks are so-called server-side attacks, where the attack is happening on the side of the global server, which gets all the updates. And here, potential attacks are regarding privacy. For example, there's been many papers that have shown that you can deduce from the global updates the actual training data. So you just take the model updates that you get in, and you can then restore the images, for example, that have been used for training by one peer. But there are also other attacks, like the availability of the whole training procedure can be tampered with, because the parameter server, if it's not available for sharing updates, then the whole federated machine learning process doesn't work. So what we do in this project, in the overall vision, is rethink how federated machine learning is done, and go from a centralized approach, which uses this global untrusted key value server, or the parameter server is often implemented as a key value store, with a more decentralized model based on blockchains. And the main goal here is really to mitigate these attacks that I've mentioned before. And I don't want to talk too much about the attacks, but maybe briefly mention a bit the intuition why it helps to use blockchains in the next slide. But we focus on a first step that is needed to make this happen. So what are the challenges that we are working on? The first challenge is clearly everybody knows who uses blockchains as a decentralized platform, that it's pretty heavyweight and slow. So meaning that the throughput that you get from blockchains for reading and writing to the blockchain is very low. And this is actually an issue for federated training and can slow down the overall process. So as a first challenge, we work on that. And this is actually the highlight that I'm going to talk later on, how to increase the performance of blockchains to make them usable as a decentralized key value store for federated machine learning. The second part is then that we want to attack or develop techniques to detect the attacks that I mentioned before. And just one intuition why we use blockchains, for example. One idea is that we record during the training all updates that happen. So which data has been used by using some hashes, and how the updates look like, to trace back who was actually poisoning, for example, the model. So we make use of this distributed ledger aspect of blockchains to really trace all this information and make it unmutable. But as I said, let's focus on the first part of the talk, which is the results that we've been working on now since the last year, and that we've been publishing at SIGWAD and BLDB 2019. So if you look from the outside at blockchains versus scalable key value stores, you see that on the one hand, blockchains provide a very low throughput of only tens of updates per second, while key value stores can provide much higher update rates and thus are much more suitable for really training in such a federated setup. Because very often in such setups, thousands or even millions of parameters are updated and need to be sent to the parameter server. The second problem of blockchains versus key value stores is, in a federated learning scenario, you might have multiple clients or multiple peers that want to share training data. And if you add more nodes in a key value server, you can increase the throughput and so serve more clients. But with a blockchain, that is not the case. Simply adding more nodes does not increase the throughput, but might even, in some cases, decrease the throughput. So what our challenge is to get these blue lines and blue bars to the green side with the properties of blockchains. So keep the properties of blockchains, but get the performance of native key value stores. How do we do that? The idea is that we use blockchains as on the storage layer. So we write the updates during federated learning into a blockchain network, but implement a key value store layer on top to improve the performance and implement performance optimizations. So how does that look in detail? As I said, the storage layer is used as a tamper-proof storage for all updates that happen during training, and we use the typical blockchain protocols without changing in a permission setup, for example, for replicating data to different peers, and also doing distributed aggregation on those parameters. And the key value layer on top implements typical key value techniques for performance improvements. And here we do things like sharding, partial replication, and changing consistency levels if that is suitable for the learning process. And I'll talk about the two first ones here in a quick overview to give you an idea how they actually help to improve the performance. So what is sharding about? So sharding, how we implemented it in Blockchain TV, which is our blockchain-based key value server, is that we distribute the operations that happen during learning, so meaning put and get operations of clients across multiple blockchain networks. So we can parallelize them across multiple shards, and each shard is implemented by a separate blockchain network. So whenever a put is coming in, we first compute a partitioning function, such as a hash function, and decide where to route the request to, and then either serve it by one or the other shard, or we can even support many more shards. In a nutshell, what that gives us is if you add more shards to your storage layer, you can improve throughput. And what you see here is just a small measurement we did in a setup where we increased the number of shards from 2 to 4 to 8, and you see perfect linear scale up, where you can get in this setup already from 50 operations per second to 300 operations per second, just writes, and writes are more expensive in blockchains than reads. So this is really, let's say, a challenging workload in terms of blockchains. And the question is now, is that everything we need? And the clear answer is no. We implemented many more techniques, and let me go in a second one, which is motivated by that slide. So you see here, multiple shards help to improve the overall performance, right? You see here, if you add more shards, you get a linear scale up. 1, 2, 4, 3, 1, 2, and 3 shards always improve it. But if you add more peers, which is shown here on the x-axis, the throughput stagnates or sometimes even drops in certain situations. So meaning the scalability issues with a number of peers is not yet solved by simply sharding. And the main reason here is that all data in a blockchain is replicated to all peers. So what we do in our blockchain-based key value server instead is, instead of full replication, we introduce partial replication protocols. that allow us to define what is the replication factor for each shard, and thus also improve the performance with the number of increasing peers, because we can control the overhead that come with an additional peer, and we don't need to synchronize all data to all peers. So the replication factor here is an interesting tuning parameter where you can that you can use for higher, so to say, trust or higher performance. And this is also shown on the next slide. Actually, what these two parameters, sharding and partial replication, give us is that the blockchain key value server can mimic everything, every behavior, the behavior of a native blockchain that uses one shard and full replication, which is here shown as a high trust plot, where we increase the number of peers, and you see, okay, the throughput is not increasing that much, but that is the behavior of a native blockchain. Or we can get the, let's say, the performance of a key value server, or native key value server, if we use multiple shards and really reduce the replication factor to 1, so no copy is kept. But then you lose kind of all trust, because now the consensus is the consensus of one node, which doesn't give you much. But the message here is that you can get everything in between with blockchain KV. You can configure it, let's say, with a certain replication factor to get a certain, let's say, level of trust. And you can also configure it to use multiple shards to improve the performance. And here we just see between the green and blue line, this is the spectrum of configurations that we can support, and thus trade, let's say, trust versus performance. So what you've seen is our work on making blockchains more performant, more scalable, by building a key value layer on top of existing blockchains. Ensure there is more than the techniques that we presented here in this talk. So in the paper, there's more on additional, let's say, off-chain protocols. Since we add a new layer on top of blockchains, we introduce new, let's say, attack surfaces. So you still need to do some additional work if you build a layer on top of a system. And this is also in the paper. And the second thing, there are more ideas on how to use lower consistency levels on blockchains to reduce the latency, because latency is another issue. I just showed throughput today. And so future work, as I said, now we have this scalable key value server, and the next work where we actually are already working on a follow-up submission to ICDE, which is another top conference this year, and hopefully make it. The deadline is in a week, where we think about how do we use actually these sharding possibilities that we now have to mitigate attacks on privacy. Because if you intelligently shard the global model across peers, none of the peers is really seeing the full global model. And now the question is, if you don't see the full global model, you can use this to actually prevent privacy attacks. And so this is a paper, as I said, that is currently being prepared for submission, and hopefully first we'll finish it before the submission deadline, and more hopefully that we will get it into the conference.